Hi boys and girls, this is lecture 4.2 in Unit 4. The topic, concavity and the second derivative test. In this lecture, we're going to learn how the second derivative can give us information about the graph of a function. Let's start with a definition of concavity. Let f be differentiable on an open interval I. The graph of f is concave upward on I if f prime is increasing on the interval, and concave downward on I if f prime is decreasing on the interval. Notice that it's saying f prime is increasing or f prime is decreasing. The first derivative, increasing or decreasing, means we're talking about the slope of the first derivative, which of course is the value of the second derivative. So the second derivative gives us information about the slope of the first derivative, and that's how we're going to determine concavity. Now let's also talk about visually what concave up and concave down looks like. A portion of the graph which would kind of look like a cup, it would hold water, is concave up. A portion of the graph which kind of looks like an upside down cup, it wouldn't hold water, is concave down. Now let's see how we will test for concavity using the second derivative. Let f be a function whose second derivative exists on an open interval I. If f double prime of x, the second derivative, is greater than 0, positive, for all x in that interval, then f is concave up in that interval. So if f double prime is positive, you're going to have a section of the graph that looks like that. If f double prime of x is less than 0, the second derivative is negative for all x in I, then f is concave downward in I. So if f double prime is negative on a section of the graph, you will have second derivative negative, you will have a downward facing portion of the graph. Now we're going to pretend like this L isn't here. I noticed the typo, you noticed the typo, but it's all gone now. Analyzing a curve using the second derivative. Let's take a look at this graph, determine the concavity at various sections of the graph, and what that means as far as the second derivative. Notice the green section of the graph. This is a portion of the graph that's concave down. It's like a cup that's upside down. We would find that if we took the second derivative at any point along the curve here, it would be a negative number. Look at this purple section of the graph. It's concave up. It's like a cup that would hold water. If we took the second derivative at any point along the curve here, we would see that the second derivative is positive. Let's take a moment to remember what we would expect to see from the first derivative as far as this particular curve is concerned. On this section right here, we have an increasing portion of the graph. The slopes are positive here, so we would expect the first derivative to be positive on this section of the graph until it reaches this maximum value, where we would have, of course, a horizontal tangent line. The slope, or the first derivative, would be 0 at that point. And then on this section of the graph, the slopes are negative. It's a decreasing portion of the graph, which means the first derivative would be negative on this section until we reach this minimum value, another horizontal tangent line where the first derivative would be 0. And then in this last section, we have increasing slopes, and therefore we would have our positive slopes, an increasing portion of the graph where the first derivative would be positive. So notice that these sections that are defined by the critical numbers that we found from the first derivative are different sections than those determined by the second derivative. The first derivative gives us information about the slopes of the curve, increasing or 0 or decreasing, and the second derivative gives us information about the curvature of the curve, whether it's concave down or concave up. We will learn to analyze a curve using the first and second derivatives in order to get all of the information about the curve possible from those values. Here are some guidelines for finding intervals of concavity. Let f be continuous on the interval AB. To find the open intervals on which f is concave up or concave down, use the following steps. Locate where f double prime of x is equal to 0. So we would have to take the first derivative, then the second derivative, and set the second derivative equal to 0. Or find where the second derivative is undefined in that interval. And we will use these numbers to determine test intervals for concavity. Very similar to what we did with the first derivative, except we would be using the second derivative. Determine the sign of the second derivative at one test value in each of these intervals, and then use these results to determine whether f is concave up or concave down on each interval. Find the open intervals on which f of x equals 6 over x squared plus 3 is concave upward or downward. We know that to determine concavity, we're going to need the second derivative. But in order to find the second derivative, we'll need to start with the first derivative. So let's find that. First of all, I'm going to rewrite this function as 6 times the quantity x squared plus 3 to the negative 1 power. Then, using the power rule in conjunction with the chain rule, I'm going to have negative 6 and then x squared plus 3 to the negative 2 times the derivative of what's inside, which is 2x. Multiplying these two together and dropping this section to the denominator gives me a first derivative of negative 12x over x squared plus 3 quantity squared. Now, in order to take the second derivative, I am going to have to use the quotient rule. So it will be the denominator, x squared plus 3 quantity squared, times the derivative of the numerator, which is negative 12, minus the numerator, negative 12x, times the derivative of the denominator, which is 2 times the quantity x squared plus 3 to the 1 power times the derivative of what's inside, which is 2x. And of course, all of this is over the denominator, x squared plus 3, squared, which now makes this to the 4th power. I'm going to factor out a few things. Notice that both of these terms, this one and this one, have an x squared plus 3 term that I can factor out, and a negative 12. So let's rewrite this, factoring out those two terms. I'll have negative 12, then times x squared plus 3. What's left in this first term when I take the negative 12 and one of these x squared plus 3's is just 1 x squared plus 3. What's left in the second term will have minus, since we took out this negative 12 and put it in front. There will be an x left, a 2, and a 2x over here. This isn't a negative, it's a multiplication symbol. So the x and the 2 times 2x will give us 4x squared. Since this canceled when we factored it out at the beginning, all over x squared plus 3 to the 4th power. Notice that this x squared plus 3 will cancel with one of these, so simplifying gives me negative 12. This cancels, and that's going to leave in the numerator negative 3x squared plus 3, and now in the denominator we have 3 of these. And one final simplification at this point. I'm going to pull out a negative 3 out of this term and multiply it by the negative 12, giving us a 36 times x squared minus 1 all over x squared plus 3 to the 3rd power. And that is the second derivative. Let's take this to the next slide. We have 36 times x squared minus 1 over x squared plus 3 to the 3rd power. Again, that is the second derivative. We know that now we need to set it equal to 0 in order to generate test intervals to determine concavity. We can also look at places where it's going to be undefined. Even though this is a rational function, this denominator will never be 0. We can see that since we're squaring the number that we put in for x, that will be a positive number added to 3, some other positive number, but this denominator will never be 0. However, when we set the numerator equal to 0, we will get a couple of values. Dividing by 36 doesn't change the right side of the equation, it's still 0, and solving here gives us two values, plus or minus 1. So we're going to use these numbers to set up our test intervals. We'll go from negative infinity to negative 1, then negative 1 to positive 1, and 1 to positive infinity. Very similar setup to what we were doing with the first derivative, except that now we're going to be checking for concavity. I will need to know what the second derivative is at each of the test values that I choose in these intervals. I'll choose negative 2 here, I'll choose 0 in this interval, and I'll choose 2 here. The sign at each of these points will tell me the concavity in each of these intervals. So f double prime of negative 2 is 36 times negative 2 quantity squared minus 1 over negative 2 quantity squared plus 3 cubed. Well, squaring this negative number makes a positive 4. Minus 1 is 3 times 36 is a positive number. And in the denominator, positive 4 plus 3, this is also going to be positive. Remember, we don't care so much about the value of the second derivative here, but the sign is what we're looking for. And since the second derivative is positive at this number, this interval is concave up. Now let's look at the second derivative at 0. We end up with 36 times 0 minus 1, which is negative 1, over 0 plus 3 cubed, which is 3 cubed. That is negative over positive, which of course is a negative number. Meaning on this interval, our graph is concave down. And now let's look at f double prime at 2. 36 times 2 squared minus 1 over 2 squared plus 3 quantity cubed. This is going to be a positive number times a positive number, and the denominator is also going to be positive, giving me another positive number in this interval, meaning that, of course, we have a concave up section of the graph. Now let's take a look at the actual graph to see if it verifies our analysis. And of course it does. If you look at a negative 1 here, which is about right here, you can see at this point that it's changing from a section of the graph that is concave up, a section that would hold water, to a section that is concave down. And then of course at positive 1, you see that change happening again. This little section is concave down, and again that's what our analysis shows, and then at this point it becomes concave up again. That's how you use the second derivative to determine concavity on a function. Perhaps you've been wondering what you call it when concavity changes on a graph. We know that when the slope changes on a graph, we have extrema, a max or a min. But what about the place where a graph is changing from concave down to up, or vice versa? That is called a point of inflection. Points of inflection are places where concavity changes, and points of inflection occur where f double prime of x equals 0 or where f double prime of x is undefined. So in the previous example, when we set the second derivative equal to 0 and we got 1 and negative 1, those were points of inflection on that graph, points where the concavity is changing. On this graph, if we were estimating where that would happen, we see that this graph is concave down, concave down, concave down, and then looks like it's switching concavity here. It's changing to concave up, and then perhaps around here, it looks like once again it's changing to concave down. And then there's one more change, perhaps occurring about right here, where it goes concave up again. Now, if we had the equation for this function, the second derivative would be 0 at these places, and that would indicate where those points of inflections are. Let's determine the points of inflection and discuss the concavity of the graph of f of x equals x to the fourth minus 4x cubed. We will need, of course, the first and second derivative, so let's take the first derivative. This gives us 4x cubed minus 12x squared. And the second derivative then will be 12x squared minus 24x. So nice to take derivatives of polynomial functions. Setting the second derivative equal to 0 and factoring out the 12x gives us two factors which will generate points of inflection, 12x and x minus 2. 12x equals 0, of course, gives us x equals 0, and x minus 2 equals 0, of course, gives us x equals 2. So let's set up our intervals with these values, negative infinity to 0, 0 to 2, and 2 to positive infinity. I'll pick a test point in each of these intervals. I'll choose -1 here, 1 and 3 here. Now I'm going to need to know what the second derivative or the sign of the second derivative is at each of those test points. So f double prime of -1 is going to be 12 times -1 squared minus 24 times -1. This is going to be 12 plus 24, which of course is positive. That means we'll have a concave up section of the graph from negative infinity to 0. Now let's find the second derivative at 1. That's our test point in this interval. We'll have 12 times 1 squared minus 24 times 1. That's going to be 12 minus 24, a negative number. So in this interval, we're going to have concave down section of the graph. Now let's look at the second derivative at our final test point, which was 3. That means we'll have 12 times 3 squared minus 24 times 3. This will be 9 times 12, which is 108, minus 72, positive number, which means we'll have a concave up section of the graph. Let's take a look at the graph as usual to see. It might kind of be, yes, there we have it. Pretend like there aren't annotations all over it, and let's see if we can find our intervals. We have 0, 0, and our analysis says that the graph should be concave up until we get to 0. As you can see, it is. At 0, the concavity changes. Our analysis says that our graph should be concave down from 0 to 2. Well, here's 2. So we're looking for a concave down section of the graph to here. And notice it is concave down. And then once again, it changes to concave up for the rest of the curve. So the graph is verified by our analysis once again. Now let's discuss the second derivative test. The second derivative test is a way to tell whether or not a value is a max or a min. Before I read the definition, let's look at these pictures. Let's imagine that c is a critical number. We know this because f prime of c is equal to 0. We found that the first derivative at c is 0. There's a horizontal tangent there. We just don't know if it's a max or a min value. We can actually use the second derivative to see if it's a max or a min. Because if the second derivative is negative there, a negative number, that means at c you have a concave down section of the graph. That means that c must be resting at the top of a hill. That means it's a max. Similarly, look over here, we have c again. It's a critical number. We know this because the first derivative at c is 0. Let's put c into the second derivative to find the sign there. If it's positive, greater than 0, that means that that's a concave up section of the graph there. That means c must be resting at the bottom of a valley because it's concave up there. Therefore, it must be a min. So when you have a number and the first derivative is 0 there, the second derivative is negative, it's a max. And if you have a critical number, the first derivative there is 0 and the second derivative is positive, then you have a min. And that's what this definition says. Let f be a function such that f prime of c equals 0. In other words, c is a critical number because the first derivative is 0 there. And the second derivative of f exists on an open interval containing c, our critical number. If the second derivative at c is positive, then f has a relative minimum value at that point. If f double prime, the second derivative, is negative, then f has a relative maximum value at that point, c. And if f double prime of c equals 0, if the second derivative at this potential critical number is 0, the test fails. That is, f may have a relative maximum, a relative minimum, or neither. You won't be able to tell whether it's a max or min if the second derivative there is 0. In such cases, you can use the first derivative test. Remember, the first derivative test has us examining the behavior of the first derivative on either side of the critical number to determine whether it's a relative max or min. So both of these tests will help us with that information. In our last example, we're going to use the second derivative test to find the relative extrema for f of x equals negative 3x to the fifth plus 5x cubed. In order to find extrema, we'll take the first derivative and set it equal to 0, which will generate a list of critical numbers. Then we'll find the second derivative and determine concavity at each of those critical numbers. This will tell us if they are maximum values, minimum values, or neither. But of course, we begin with the first derivative. Our first derivative is negative 15x to the fourth plus 15x squared. I'm going to set this equal to 0 and factor out negative 15x squared. This leaves x squared minus 1. As I continue to factor, I end up with negative 15x squared, x minus 1, x plus 1. Each of these factors will generate a critical number when set equal to 0. 0 is one of my critical numbers. Of course, 1 is another. And the last one will be negative 1. So I have a list of 3 critical numbers. Are they maximum values, minimum values, or neither? We won't know until we use the second derivative test. So now we'll find the second derivative. F double prime of x is negative 60 x cubed plus 30x. Let's take out a negative 30x. This leaves 2x squared minus 1. That's our second derivative. We will need to know the sign of the second derivative at each of these points to determine concavity. So let's get that information. F double prime of 0 is going to be negative 30 times 0 times 0 minus 1, which is essentially negative 30 times, well, I guess we already can see that it doesn't really matter what anything else is. That is going to be 0. Interesting. This is not a positive number or a negative number. So for the second derivative equaling 0 here, we have no conclusion. We can't tell if it's a max or a min value at 0. What is the second derivative at 1? We have negative 30 times 1, and then 2 times 1, which is 1 minus 1, is 1. That is a negative number. A negative number at 1 means we have a concave down section of the graph, meaning 1 is sitting at the top of a hill, making it a maximum value. And finally, let's find the second derivative at negative 1. We'll have negative 30 times negative 1. Of course, negative 1 squared is a positive 1 times 2. 2 minus 1 is 1. Negative times positive is a positive number. So at negative 1, the graph is concave up, which means negative 1 is sitting at the bottom of a valley, making it a minimum value. So let's, as usual, take a look at the graph and see if we have correctly analyzed our data. So at 0, notice it's not definitive. It's not a max or min value, and we weren't able to tell from the second derivative test anyway. At 1, we found that the second derivative was negative, which meant that we had a concave down section of the graph and we had a maximum value there. And at -1, the second derivative was positive, meaning we had a concave up section of the graph, which meant that at -1 we had a minimum value. Win, win again. And that's it for today's lecture. God bless you, boys and girls.